Hello students, welcome back to my channel Explore Physics, Let's Explore. Hope you all are doing well. Today I am going to explain you about the phenomena electromagnetic induction. You know that whenever there is an electric current flowing in a conductor, a magnetic field is also produced in it. The reverse of that is also true. Whenever there are magnet or magnetic field, that can also produce the electric current. So, this phenomena where the electricity is produced or electric current is produced because of magnetic field or magnet is called electromagnetic induction. We are going to discuss everything about the electromagnetic induction today in this class. So without further delay, let's start the class. So as I told you, whenever there are magnets, electricity is also produced. Let's understand it with an example. Say we have one wire AB which is placed between the two poles of a horseshoe magnet. North and south are the two poles, and this wire, the two ends of the wire are connected to an instrument which is called galvanometer. It has a pointer. So this is the instrument which only detects the flow of electric current in a circuit. How much electric current is flowing in the circuit? That is given by ammeter. We have already discussed it. But galvanometer shows us only the presence of electric current in a circuit. So what we are going to do, if I am going to rapidly move it up, if I am going to rapidly move up this wire, I'll see that this galvanometer, which was the pointer was at when there is no current, the pointer is always at the center. So I'll see that when I'm rapidly moving this wire up, this galvanometer shows the direction to one side. And I'm going to rapidly moving it, then it is deflected to one side. If in the next step, if I'm going to, push it down, or I'm going to rapidly moving it down, the deflection is to the other side. So now the deflection is to the other side. So what I have observed that when I'm moving it up, when I'm rapidly moving this wire up, the deflection of the galvanometer shows one side, the direction of electric current. If I'm moving it down, the deflection shows to the other side, showing that the direction of electric current is changing. When I am moving it up, it is in one direction. When I am moving the wire down, it is to the other direction. If I am moving it rapidly up and down, then it is moving to and fro. Then the pointer will move to and fro if I am moving the wire up and down rapidly. So this shows that after every half a cycle, when it is moving up, the direction is to one side. When I am moving it down, the direction is to the other side. So the direction of the electric current keeps on changing. This current is the alternating current, or we just simply write it AC, which keeps on changing its direction, and it is induced. The current is induced because of this rapid movement of wire. This is actually known as induced current. So we have induced the current in the circuit by moving the wire up and down. So this is one activity which shows generation or production of AC or induced current. What did we do? We have placed the wire AB between the two poles of horseshoe magnet. We have moved it up. The deflection in the galvanometer shows one side. When we are moving it down, the deflection is to the other side. When we are moving vigorously up or rapidly up and down, then the deflection is, the pointer moves to and fro, showing that the direction of current is changing every half a cycle. And this is called alternating current. And this type of current is also known as induced current because of this electromagnetic induction. This is the example of, or the activity which shows or demonstrates the electromagnetic induction. Right? This is one activity. I can just write activity 1, which shows or it demonstrates the electromagnetic induction or the production of induced current. So what happens here, when we are just moving it up and down, the magnet is fixed, but only the wire is moving. So there has to be a relative motion between the magnet and the wire or the conductor. Then only the induced current is produced. So there has to be a relative motion. Here the magnet is fixed, only the wire is moving. Then we can show or demonstrate the electromagnetic induction and the production of induced current. The strength of the alternating current thus produced can be increased by increasing the number of turns. If I am taking a coil which has more number of turns, definitely we'll get more amount or strength of induced current. We can also make it more stronger by taking more stronger magnet here, and we can also change the direction by changing the polarity of magnetic field. We can also make the induced current more stronger by winding the coil on a soft iron core. So there are different ways where I can increase the amount or the strength of induced current. I can also show or demonstrate electromagnetic induction by the second activity. So I am naming it as activity 2. So where I will be taking one coil and the two ends of the coil are attached to a galvanometer. Here I will be taking one bar magnet. Say this is north and this is south of the bar magnet. So what I'm going to do, I'm going to just insert one end of the bar magnet inside the coil. So here I'm going to insert this bar magnet inside the coil. I see that the galvanometer deflects to one side. When there is no movement, then the pointer will be at the center, showing no electric current flowing in the circuit or no electric current flowing in the setup. When I'm going to introduce or insert that or push that magnet inside the coil, I'll see that the pointer is deflected to one side. Okay, and the deflection is only for the moment, so it will show you the momentarily deflection. So what did I say? When I'm going to introduce or push this magnet, the north side of the magnet inside the coil, this will show the deflection to one side momentarily, showing the production of electric current. I'll be explaining you the reason also, but the first step, then when I'm going to push it inside the coil, I'm going to push the bar magnet inside the coil, the deflection is one side of the galvanometer. If I'm going to hold it here, in the second step, if we have taken it inside and it is held here, this is first point. The second point is when I'm holding it inside the coil, I see no deflection. So this pointer will come again to 0, showing that there is no electric current in the flowing in the coil. Third, what I'm going to do, I'm going to pull out the magnet. I'll see the deflection in the galvanometer for a moment, so momentary deflection, but to the other side. So 3 steps are there. One, I'm going to introduce or push the magnet inside the coil. There will be a deflection in the coil. When I'm going to hold it there within the coil, no deflection means no current in the coil. When I'm going to pull it out, the third step, when I'm going to pull out the magnet, I show the deflection but to the other side. So why does it happen? When I'm going to push it inside the first step, what will happen? Again, because of the relative motion between the coil and the magnet, here the coil is fixed, the magnet is moving, the deflection, the momentarily induced current and flow in the circuit. Second, it becomes steady. Now first, because of this, the electric current is flowing, induced current is flowing, and the second, when the magnetic field is steady, there is no motion between the coil and the magnet, so no current will flow. Third, when I'm going to pull it out, the magnet is pulled out, again there is a change in the magnetic field when I'm taking it out, so again the induced current will flow but in the opposite direction. If I'm going to do it vigorously, pulling and pushing, pushing and pulling, then of course there will be continuous change in the current, and the pointer keeps on deflecting to and fro. Again, the alternating current will be produced. This demonstrates the phenomena of electromagnetic induction. I hope this activity 2 is also clear to you. Now we'll talk about activity 3. What happens there? We have discussed in first activity when the wire was moving and the magnets there was no movement, magnets were stationary. In the second activity, we have seen when the magnet was moving but the coil was stationary. Now the third activity, again to demonstrate the phenomena of electromagnetic induction and production of induced current, we will be taking two coils. Say this is coil A, and we have the switch here or the key, and here it is connected to a battery, right? So we have this is coil A. We have one more coil which is placed close to this coil, and now we'll see what will happen. This A is called primary coil and this B is called secondary coil. This B is called secondary coil. Now what will happen when I'm going to switch it on or press the key? What will happen? Because of this, electric current will start flowing in coil A. Because of this, the magnetic field will be produced, and this B will be under the influence of that magnetic field. Same thing, like we are pushing the magnetic field, the same thing will be observed, and here the deflection will be shown to one side of the galvanometer. Now, if I keep on pressing it, it's on only, then I'll see there is no movement or no deflection, means no induced current is flowing in coil B. If I'm going to release this or it is off, then what will happen? Again, there will be a deflection in the galvanometer showing the production or the induced current, but into the opposite direction. So again, 3 steps. 1, when I have switched on the coil here, when I have pressed the key, electric current will start flowing in the primary coil. Because of this, magnetic field will be produced. This comes under the influence of magnetic field, and the induced current will be detected by the galvanometer. Deflection is to the other side. When I keep on pressing the key or the circuit is on, there is no deflection in the coil, means no current is induced in the coil. Third, when I am going to release it or the circuit is off, again I see the momentary deflection here in the galvanometer showing the direction is to the other side. So the direction of induced current is to the other side. If I keep on pressing and or putting it on or off the switch, then I see the deflection in to and fro direction. Again, because of this change of direction, we'll see that is the production of induced current, all the alternating current, and this shows the phenomena of electromagnetic induction. Here, there is no motion. Out of these two, no coil is moving. But because of this production of magnetic field only, the current is induced. So this is the third activity which shows the phenomena of electromagnetic induction and the production of alternating current or induced current. Again, the strength can be increased by taking more number of turns. This is used for making the transformers, step up and step down transformers. The number of coils, more number of coils in A primary coil or more number of coil, the turns in coil B will give rise to the step down and step up transformer. Step up transformer means when the voltage is made higher. Step down is when we are going to decrease the voltage of a circuit. So by changing the number of coils in A and in B, we make the step down and step up transformer. The same concepts application is used for making the transformer. To make the generator, we use the first activity where the wire is moved up and down. So instead of wire in the generator, we take the coil which moves up and down. Again, the number of turns in the coil increases the power of the generator. So this is all about the electromagnetic induction, its application, induced current and alternating current. That's all for the day. Stay safe, stay healthy, and a very big thank you to you all. Please subscribe my channel, like and share if you like the content. Thank you and bye-bye.